Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall be discussing the topic of springs. Figure 2.1 is the extension load graph for a light spring S. State the range of loads for which S obeys Hooke's law. So, in order to figure out the range in which Hooke's law is obeyed, we need to figure out the part of the graph that is linear. So this part here is linear. And then after that, the graph curves up like this. Hooke's law states that there is a linear relationship between the force and the extension, F equals Kx. So therefore, the linear part is the part that obeys Hooke's law. And we can say that it obeys from 0 to 8 newtons, of course. Up to this number here. This is where Hooke's law is obeyed. Using information from figure 2.1, determine the spring constant of spring S. So you can just take any point on the curve. For example, I chose point P, which is this blue point here. For point P, the force is 8. This is F, and the X is 15. So that's why I chose point 815. And I wrote 815 like this. So and then F equals Kx. If we want to get K on its own, we can divide by X on the other side like this. So K becomes F over X. We said that the F is 8 and the X is 15. How did we get that? We got that from the graph. So this is load per Newton. So this is the F and this is 8. And this is extension in centimeters. So X is 15. So therefore, we have 8 over 15, and that's the final answer, 0.53. A second spring identical to spring S is attached to spring S. The two springs are attached to a rod, as shown in figure 2.2. A load of 4 newtons is suspended from the bottom of spring S. The arrangement is in equilibrium. State the name of the form of energy stored in the two springs when they are stretched. Of course, this is elastic potential energy or strain energy as well. You could have written strain energy, but it's most commonly known as elastic potential energy. Determine the extension of the arrangement. So in this case, we have a spring pulling another spring. Now, since the spring constant is 0.53, and since the force is 4 newtons, you can think of it this way. This is 4. And the K is 0.53. So the extension is going to be how much? So the extension is going to be 15. Because if you divide 4 divided by 0.53, you get 7.5. So let's write down the equation here, F equals Kx. So we want the extension, so X equals F over K. And then the force here is 4. The K is 0.53. If you divide 4 by 0.53, you get 7.5. But this 7.5 is the extension of the first spring only. So this spring will extend by 7.5. And this spring will exert a similar force on the upper spring. So the upper spring will also extend by 7.5 as well. Therefore, the total extension here is going to be 7.5 times 2. So how did we get this 15? We did 7.5 times 2 because there are 2 springs, which is 15 centimeters. Next, we're told the load is carefully increased to 6 newtons in total. Calculate the distance moved by the load to the new equilibrium position as the load increases from 4 to 6. So first of all, we start with the 6 newtons and we repeat the same process again. If you can write 8 over 15 or you can write 0.53 for the value of K, it doesn't matter. So you can just write F equals Kx, X equals F over K, which is 8 over 15, which is 6 over 0.53. So therefore, if we divide 6 by 0.53, we're going to get 11.25. Again, this only applies to one spring, so we can multiply it by 2 to get the total. and that's the new total. So the difference is 7.5. How did I get that difference? I subtracted these two values together. So 22.5 minus the old extension, which was 15, and that gave us 7.5 centimeters. Figure 3.1 shows part of the extension load graph for a spring. The spring obeys Hooke's law between points A and B. On figure 3.1, complete the graph between A and B. So since this is part of the graph that obeys Hooke's law, the graph is going to be linear. There will be a straight line joining A to B because this is the definition of Hooke's law, which is F equals Kx. There is a linear relationship between the force and the X. State the name of point B. Of course, the last point in the region that obeys Hooke's law is called the limit of proportionality. So this point here is at the end of the region of Hooke's law, and this is called the limit of proportionality. Next, the average value of the load between A and B is 6. Calculate the work done in extending the spring from A to B. So to extend the spring from A to B, the graph tells us that the extension here is 3 centimeters. So we need to first convert that into meters. So that becomes 3 divided by 100, and this is 0.03. So that's the extension or the distance traveled. And since work is force times distance, and we know that the force is 6, so force equals 6, distance equals 0.03. So the work is 0.18. In C, we're told that the spring has an unstretched length of 4 centimeters. And when an object is hung, the length increases from 4 to 6. Calculate the mass of the object. So to increase from 4 to 6, that means it increased by 2 centimeters. And since we went from 4 to 6, we say that x equals 2 centimeters or 0.02 meters. But in this case, we don't really need to convert to meters because everything is given in centimeters. So we can just work in centimeters to begin with. So now we want the mass of the object. So what's the mass of the object here? So the mass of the object is the responsibility of the force. It's like the source of the force. So how do we get the mass of the object in this case? We need to first get the force. So how do we get the force? So first we need to get the K. We have F equals Kx. From the graph, we can put the F as 12. We already have that value in the graph here, right there. And we want to get the value of K. So we put X at the corresponding value of X, which is 3 on the graph as well. So therefore, 12 equals K times 3. And we get K as 12 divided by 3, which is 4 newtons per centimeter. So we're working in centimeters anyway. So we don't need to do any conversions like we said before. Now that we have the extension as 2 centimeters, this is there, we can simply get the new force as K times X. So 4 times 2, which is 8 newtons. Now that we have the force, we know that this force is because of the weight of the object. So we divide it by 10 because W equals mg. So the 8 newtons here would be the W. And we want to get the M. And we know that G is 10. So therefore, 8 divided by 10 gives us the value of the mass, which is 0.8 kilograms. The object is immersed in a liquid but remains suspended from the spring. The liquid exerts an upward force on the object and the length of the spring decreases to 5. Calculate the upward force exerted on the object by the liquid. So in this case, the object is between two things here. It's between the spring and it's in a liquid. So because of the liquid, there is a force pushing up. And at the same time, there is the force by the spring. And these forces are equal to each other. So we want the upward force exerted on the object by the liquid. And this would be, so let's write down all the forces that are acting on this object here. So this object here has a weight pulling it downwards, and it has upthrust force, we call it FU, and it also has spring force. So the spring, we already know the K for the spring is 4, and in order to get the force by the spring, we simply say that F equals Kx again, and we want to find the extension here. So the unstretched length is 4, and in equilibrium, they told us that the current extension, like the final extension, is 5. So basically, the extension is 5 minus 4, which is 1 centimeter. And since the K we already know is 4 newtons per centimeter, this is 1 centimeter, this is 4 Newton per centimeter. So if we multiply these together without doing any conversions, we get 4 newtons. Therefore, the force by the spring is equal to 4. We already know that the weight is equal to 8. And we want to get the upthrust force, which is upwards. So upthrust force, this is in equilibrium in a sense. We have 4 up and 8 down. So we have to have 8 minus 4 as FU. Hence, the final answer would be 4 newtons, because the total upward force must be equal to the total downward force, since it is in equilibrium. Okay, so in A, we're asked to state Hooke's law. Hooke's law stipulates that the extension of a spring is directly proportional to the applied force, or F equals Kx, but you should write it in words, not only write the equation. For B, we're told for forces up to 120 newtons, a spring obeys Hooke's law. A force of 120 causes an extension of 64. Draw the force extension graph for loads up to 120. So when the force is 120, so how do we get the 120 here? We have to count the squares. Here we have 10 squares, leading up to 50 newtons. So 1 square equals 10 newtons. So therefore, in order to get, excuse me, I'm sorry, I apologize. So 10 squares go to 50 newtons. Let's rewrite it down. Therefore, 1 square goes to 5 newtons. My apologies. 1 square here goes to 5 newtons. So this would be, the first square here would be 105. Second square would be 110. We want 120, so it will be square number 4. And we draw a horizontal line like this. And then the vertical line has to come from 64 millimeters. Again, between these two, we have 10 boxes. We have 20 millimeters. So 1 box equals 2 millimeters. We want 64, so we want 2 boxes after the 60. This is where we would get the 64. And if you extend this line upwards, they meet at this point right here, which is 64 in X and 120 in Y. So therefore, this is the point that we plot, and we draw from 0, 0 to this point. We draw a straight line. Then we're asked to calculate the spring constant. Of course, the spring constant here is very easy. F equals Kx. So we want to get K on its own. So this is F over X. And F is already given as 120. X is 0.064. How did I get 0.064? We have 64 millimeters divided by 1,000. So we have 0.064 meters. So the final answer is 1900 or 1900 newtons per meter. A student makes a spring balance using the spring in B. The maximum reading is 150. The student tests his balance with a known weight of 140. He observes that the reading is not 140. Suggest and explain why the reading is not 140. This is because this is beyond 120. It's more than 120. So the spring no longer functions correctly. It does not obey Hooke's law anymore. And that's why the reading is not going to be exactly 140. A chest expander is a piece of equipment used by athletes in a gym. Figure 2.1 shows a chest expander that consists of 5 identical springs connected in parallel between 2 handles. Each spring has an unstretched length of 0.63. 2 athletes are stretching the chest expander by pulling on the 2 handles in opposite directions. The springs obey Hooke's law. Explain what is meant by this statement. Of course, we said that Hooke's law states that the extension of a spring is directly proportional to the force. In double I, we're told each athlete pulls the handle towards himself with a force of 1300 or 1300. State the tension in each spring. So the force is 1300. And we have 5 springs. So the force that this man is pulling with is 1300. And you have 5 springs here. So the force is divided onto the 5 springs. So each spring has a tension of 1300 over 5, which is 260. The chest expander stretches and each spring is now 0.94. Calculate the spring constant of each spring. So to get the spring constant, again, we know that F equals Kx. So K equals F over X. For one spring, we said that the force is 260. And the extension is the new length, which is 0.94, minus the unstretched length. And the unstretched length here is 0.63. So we just subtract 0.94 minus 0.63, and that gives us the answer of K. K equals 838.7 or approximately 840 newtons per meter. In triple I, we are asked to state the energy changes taking place as the 2 athletes use their muscles to stretch the chest expander. So their muscles have stored food or stored chemical energy. And then to stretch, then you have strain energy or elastic potential energy. So the conversion here is from chemical to elastic potential energy. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.